Hi, in this video we are going to talk about this problem. We are given a binary search tree and a sum. We need to find out whether there is a pair in the binary search tree whose sum is equal to given sum or not. Let's say we are given this binary search tree and we are given sum as 33. We have a pair in this binary search tree 25 and 8 whose sum is 33. That is why our output is yes. Let's see this example. We have this binary search tree. We have this sum 49. We do not have any pair whose sum is 49. We have a pair 40 and 8 whose sum is 48, but no pair with sum 49. So our output is no. Now please pause this video and write a function that takes root of a binary tree as a parameter, sum as a parameter, and it returns a Boolean value which is true if the given binary search tree contains a pair with given sum, otherwise it returns false. Let us talk about method 1 to solve this problem. Method 1 is do an in-order traversal of the given binary search tree, store this in-order traversal in an array, and then use the two-pointer approach that we discussed in the searching track. Using 2 pointers, we can find if there is a pair with given sum in a sorted array. Please note that in-order traversal of a binary search tree is always a sorted array. For example, in-order traversal of this binary search tree is 4, 8, 9, 10, 11, 20, 25 and 30. So if you do an in-order traversal, store it in an array, your array will be sorted. Now your array is sorted, you can use 2 pointers, one beginning to the leftmost position, other beginning to the rightmost position, and then you can move these pointers to find out if there is a pair with the given sum. You can refer the searching track for 2-pointer approach. The approach is explained in detail there for an array. Let us talk about time complexity and auxiliary space for the solution. The first step requires big O of n time. Doing an in-order traversal of BST is big O of n. Now second step requires big O of n time. 2-pointer approach on an array takes big O of n time. So we have 2 big O of n steps. So overall time complexity is big O of n. And how much auxiliary space it requires? It requires an array for storing in-order traversal, that's big O of n, and plus big O of h probably for the recursion call stack. So the overall extra space is big O of n plus h. Since h is smaller, we can ignore h. So overall extra space is big O of n. And if we want to be more precise about time taken, we can say first step is going to take theta n time because we are going to traverse the whole tree and then we are going to store it in an array. So it's rather than big O of n, we can say first step is theta n and second step is big O of n. Because in 2-pointer approach, you may find the pair before traversing the whole array. So overall, I can say time is theta n because theta n plus big O of n can be written as theta n. And auxiliary space for array also is theta n. You need to store the whole traversal in an array. So that much extra space is required by this solution. Now please pause this video and think of a solution that can find a pair in big O of n time. What it means is if there is a pair that exists earlier in the BST, earlier in in-order traversal, then it finds first, rather than first traversing through the whole BST and then storing it in an array and then finding the pair in an array. So please think of a solution that is big O of n. It goes theta n only in worst case. Let us now talk about method 2 to solve the problem. This method is also based on in-order traversal. In this method, we use a hash table. So the idea is this, rather than doing the whole in-order traversal, storing it into an array and then finding the pair into an array, find the pair while traversing through the array. If you find a pair at any point, you return immediately. So what we do is, we do an in-order traversal. While doing in-order traversal for every node, we check if given sum minus that node's key is already present in the hash table or not. If it is already present, that means you have a pair with given sum. If it is not present, then you insert it. So you traverse the tree in in-order traversal fashion. While traversing, you keep looking for pair and you keep inserting the node's keys. So whenever you find some minus current node key already present, you say there is a pair in the BST. So here are C++ and Java implementations of this approach. We first check if root is empty. In case your root is empty, you cannot have a pair with given sum, so you immediately return false. Then you traverse the left subtree. In the left subtree, if you find a pair, you return true. Then you check for the current node. If sum minus current node is already present in the hash table, then you return true. If not present, then you insert the current node. After that, you check for the right subtree. So if you find a pair in the right subtree, then you return true. If you do not find a pair in the right subtree, then you return false. Please note that you will come to the right subtree call only if the pair is not present in the left subtree and current node also does not form a pair. Also, one important thing about this approach does not rely on the fact that in order traversal is sorted. So this approach can be used on a normal binary tree also. In a normal binary tree also, you can use this approach to find if there's a pair with given sum. The advantage of this approach over the previous, it finds the pair, it returns true as soon as it finds the pair. So the worst case time complexity theta n, however, it can take less than theta n time in some cases. If you find the pair while doing in order traversal at the first two nodes, you will immediately return true. Let us do a dry run of this approach for this example BST. We call it for the root. Root is not null, so we go to the second step where we call for left subtree. When we call for left subtree, root is again not null. So we again call for the left subtree. This time left subtree is null. So this call returns false. So this particular function, which is for 5, has done its execution for the left child. Now it's going to check itself. It's going to find if sum minus 5 is already present or not. So it will check whether 21 minus 5, 16 is present. Your hash table is initially empty, so you will get false. What you will do, you will fall into the else case and you will insert 5 into the hash table. Right? And after that, you will call it for right of 5. And right of 5 is null. So you will get return value as false. So this is going to insert itself into the hash table and it's going to return false to its parent. Right? So this gets the control back now, and what is it going to do? It has finished with the left subtree, so it's here actually at the next line. It's going to check whether 21 minus 10 is present in the hash table or not. 21 minus 10 is 11. 11 is not present. So it's going to insert itself into the hash table. So 10 is going to be there in the hash table. Now it's going to call for its right subtree and it's going to return whatever right subtree call returns. So it's going to come here and it's going to begin the execution for this node. It's not null, so it will go to the left subtree of this. So when it comes here, it again checks whether 21 minus 16 is present or not. After calling for the left subtree basically, which is null, after calling for the left subtree, it checks whether 21 minus 16 is present or not. 21 minus 16 is present. 5 is present in the hash table. So here you get a return value true. So this is going to immediately return true to its parent. And its parent, when it sees the return value of left call, it does not do anything. It immediately returns true to its parent. And its parent, which was waiting for the last statement, whatever right call returns, that is the value it was going to supposed to return. So it returns true value because right call returns true value. So it's going to return true to the caller. So you get true for sum 21 because you have pair 5 and 16. What is the time complexity of the solution? This solution takes big O of n time because we traverse every node exactly once and until we find a pair. So we'll have to traverse at most 10 nodes, and for every node we do constant amount of work because search function and insert function both are considered constant in a hash table. How much auxiliary space it requires? It requires big O of h auxiliary space in for the recursion call stack, and then it requires big O of n auxiliary space for hash table. So overall, when we can say it is big O of n auxiliary space. So this function is big O of n time and big O of n auxiliary space.